All right, this week we're going to take on some wind circulations. We'll start with thermally driven winds, which you probably don't even realize you see them. Uh, Typically occur in the summertime, usually under high pressure or light winds, and then they become the dominant wind at that location. Sea breezes are one of the biggest ones around, and land breezes. Uh, think about it: the air over land gets hotter than the air over the water. We know that water doesn't let the air get that warm. So with that, air begins to rise over the land. Water, cooler air from the water begins to come in, taking its place. The upper air flows back out towards the ocean and back down. So it's a complete circulation. Looking in all directions, it goes up over the land, back down, outwards, aloft, and then back down to the ocean. So if you're flying into an airport that's on the ocean or near it, maybe you'll feel this when you're coming through the different elevations as you're descending into that airport. You may see the wind change direction on you. It's not going to be that strong typically. Sea breezes can run up to 20, 25 knots, or maybe even 30 knots, but that's a rare. And it's going to be in the spring when the water temperature is cold and the land temperature can get real warm. The stronger the temperature contrast between the ocean and the land, the stronger the sea breeze or the land breeze will be. The land breeze is just exactly the opposite of that circulation. Wind flows from the land back out to the ocean because the ocean is warmer at night. So one other circulation is mountain and valley breezes. These can occur all the times, but they might be accentuated sometimes in the winter. U.S. forest firefighters have to know this inside and out because they're dealing on mountains, and many times the location of the fire, how it's going to move, and all it depends really on these local wind systems. So think about it. At night, temperatures at the valleys are going to be very cold. The air is going to flow down the mountains into the valleys. As it's flowing down, it's going to keep getting colder and colder. During the day, the mountains might be a little bit warmer. They're at the top of them just sometimes. And the air might be flowing back up the valley, upwards to those mountains. So they make mountain and valley breezes. And then you can have mountain waves. And we'll take really across the Appalachians. It can happen in the wintertime or spring as the wind goes out of the northwest and they bump up and down. So let's take a look at one of these for a minute. Here's today's satellite image. And we'll bring it up into a better view of it. But notice the clouds over Pennsylvania and how they look kind of in lines, in rows, or down over Maryland there. A lot of that is the wave pattern coming off of the mountains to the west. Notice how the clouds really stop there at the mountains to the west. There's all that rising motion up the mountains causing clouds, and then they go down the mountain and they cause these wave patterns here. So you can really see them in satellite pictures sometimes. And if you were flying a plane, say from New Jersey at lower elevations, maybe 5,000 feet out across Maryland and into West Virginia, you'd be bumping and bumping, and your waves, mountain waves, would get stronger and stronger, and your turbulence would get stronger and stronger until you hit on the other side of the mountain. The wind would be coming up, but it'd be more uniform. So you get away from the wave pattern. The wave pattern is always going to be downwind. So if you had an east wind, you might see the exact opposite effect here, where the waves are more on the western side of the mountains. Just something to think about for your next flight. So let's think about now, move on to the next topic we're going to be dealing with today, and that's thunderstorms. I can talk about thunderstorms for hours, but I won't. We'll talk about thermal circulations, relatively small ones like dust devils you see sometimes. Sometimes you can see a bird soaring in the sky, just kind of floating there, never flapping its wings. It just stays aloft, or a glider. They use it all the time, these thermals. And you think about it out in the deserts where it gets really, really hot in spots and the air just flows up. Well, what happens is that stability of the air. It's hot air rises. Again, the hotter the air compared to its surrounding, if it's warmer, it's going to float up, up, and up. And the opposite could be with cold air. It might sink down. So you're going to tend to see these kind of little small circulations in the over the hot lands or ground areas. And say you have a runway, black runway, we'll say, for whatever reason, you might get a thermal over that runway because it's being so much hotter than the grass areas around it. You might have, in a really desert climate or really hot weather, a little thermal right there over the runway, causing some circulation. So now we're going to talk and move on to thunderstorms, though, as the next thing. Here's a convective sounding. Here's your wet bulb. Here's your moist adiabatic right here. Here's a dry adiabatic temperature. So this is your actual temperature, the red line. So say the temperature warmed up at the surface, to about 32 degrees Celsius. It would be dry adiabatic right to here, we'll say. Once it hit that elevation, and we're going to say it becomes saturated right there, instead of moving with the dry adiabat up, it's going to move on the moist adiabat. Notice how much warmer that temperature is than the air surrounding it. That's what you're always looking for in a sounding for whether this thunderstorm might develop. That's the area of unstable air. The bigger this area is between the actual temperature of the air and the moist adiabat, the better and better and the stronger your updraft is going to be, the more acceleration upward they're going to be, the more powerful your thunderstorm can be. One of the things to look at thunderstorms was Doppler radar. This is just a tremendous thunderstorm here. There's this little hook echo right in here. Actually, a low pressure really has developed in this little tiny area right there. And you can see the circulation on Doppler radar right there. Winds actually change direction, move in a circulation right there. So Doppler radar is a great tool for picking up thunderstorms. It's a classic hook echo here. Here's another one down here. A little bit of a hook and stuff in here. Well, here's your thunderstorm, your circulation as well. So now that we've looked at that, think about the life cycle of a thunderstorm. If you look out your window as you're flying along and see some towering cumulus, one of the things you might notice is, they keep going up, getting higher and higher very quickly sometimes. And maybe they'll merge and the updraft will increase and they'll reach even higher heights. But some days you watch out and you look out there and you'll see this towering cumulus for a while, maybe between 1 and 2 o'clock. And all of a sudden they're gone. There isn't a cloud there. What happens? Well, what happened is there's a lot of dry air above that cumulus cloud. And that cumulus cloud, all that moisture in that cumulus cloud went up into that dry air. It evaporated the cloud. You might still have some lift in there, but the air has become so much drier, it's becoming stabler, and lift is decreasing, and you're not getting the thunderstorms. But if you have enough instability and enough things to push it up it's going to go, and it's actually going to become a strong thunderstorm. And the very first thing you're going to notice after all the updraft goes up, some of that's got to start coming down next to it. So you wind up with a circulation of a good strong updraft at the beginning of the thunderstorm, and right behind it will be a very strong downdraft. And that downdraft will kind of undercut the updraft eventually with time, and it might actually kill it. Typical thunderstorms don't last more than 30 minutes to an hour at any one location. Now, what changes that is wind shear. So if you have light wind shear, you're going to get these individual thunderstorms, air mass type thunderstorms, summertime type thunderstorms, and they're going to dissipate in one location maybe every 30 to 60 minutes. However, if you get stronger wind shear, that updraft is able to maintain itself. It's not getting undercut by that cold air coming underneath it. So what happens is the warm air keeps rising and you get different cells continually developing. You get a multi-cell cluster. And if you get a really strong updraft, strong wind shear, you can get what they're called supercells, which literally rotate. And that's where your tornadoes we just looked at form. So you can see these things in thunderstorms and the life cycle. Knowing the wind shear can really help you determine what they're going to be. This is a tool that meteorologists use. Maybe you don't care about it that much, but it's just called a hodograph. All that's done is your wind direction and wind speed are plotted at every height, basically 1,000 meters up, every 1 kilometer. There's a new one of these. Here's a 1 kilometer right there. What's your wind? It's out of the north, probably about 10 knots. Oh, here's 2 kilometers. What's your wind? It's about 25 knots out of the north. Oh, here's 3 kilometers. Oh, now we've got it coming out of the northeast. And it's up to there. And you can gradually see these things rotating, going around here. So the wind speed is right here. A wind direction is up here, where whatever quadrant it's plotted in is the direction that wind's coming from. The more curved and the bigger the line is, the better chance you have more wind shear, and the better chance you'll get a supercell type thunderstorm or a cluster of thunderstorms to deal with. So you can look at a hodograph. They're on almost all the QTs. I can show you them, and you can see where these occur. Hazards with a thunderstorm. Obviously, the downdraft is a big hazard. I would not want any plane to ever fly into and out of as they're trying to land a downdraft. There's tremendous wind gusts that can occur there. Sometimes you can get derechos with winds over 100 miles an hour that have been observed. Supercells can produce downbursts of up to 100 miles an hour, plus the tornadoes. So obviously these wind gusts, and they're not just at the surface. Winds can go upwards in a thunderstorm over 150 miles an hour in a very super strong thunderstorm. So think about that. If you're flying a plane and all of a sudden you hit 150 mile an hour upward gust, your plane's not going to be doing well. We talked about tornadoes here a little bit. Hail can occur, and you don't want to deal with hail either. The stronger the updrafts, the more it can lift water droplets up, keeping them up. They keep going up and back down and rotating back into that updraft. And when they do that, they keep freezing and getting bigger. And some hailstones could be bigger than softballs. So the best place I've ever found, the Storm Prediction Center is tasked with forecasting thunderstorms. That's all they care about out there, is forecasting small-scale weather like thunderstorms. So on their webpage, there's a ton of information. So we'll just take a quick look here. I don't expect you to care all about it, but I'm going to look at it a little bit. Today, there's some thunderstorms going across Louisiana. Here's kinks in the ice up here. It's a warm front. If you were to look here at that same image, at the surface, what you see is a lot of warm air here. Temperatures up in the 80s down here, temperatures in the 50s up here. Warm air rising up, being pushed up by this front, causing a circulation right there. We've talked about warm fronts, and warm fronts tend to bring clouds over large areas. So let's go back to what that looked like on this tab. And you can see here's your cold front, a warm front here, larger area of precip. But yeah, there's some really intense thunderstorms along that front, lighter rain to behind it. So what's happening along that front then? Well, a couple things you can look at. One, you want to know how unstable it is. That area I showed you, where you looked at the area that was between the moist adiabatic lapse rate and the actual temperature, is called CAPE. The stronger the CAPE, the better chance for thunderstorms. This is a measure of CAPE right here in the red lines. So 4,000 CAPE is down over Texas being fed up into this. It's being advected in. We talk about temperature advection. We talk about moisture advection. Well, you can also have CAPE advection. And you can see the lines gathering right up into that area where those strong thunderstorms are occurring. If you were going to be flying into this area, you might expect thunderstorms to continue to develop down into this area because it's so unstable. So that's just one of the things you can take a quick peek at. Oh yeah, you want to look at wind shear? They have that as well. You got it plotted, but you can see the best wind shear is up here to the north a little bit. So the strongest thunderstorms are going to be right in this, along these wind shear areas right here. Now there's no cape back here, so there's not getting thunderstorms. You get a lot of wind shear, but without cape, you don't have any thunderstorms developing. So that's just a couple things you can look at quickly on them. Here's the sounding. Here was again that cape, that area right between the actual air temperature in the environment and the parcel air temperature. The bigger that area is, the more cape. And here's a photograph, and you can see the west winds and how they're plotted here on the map. So if you were to look at satellite images for that area, we could loop it down there as well and take a quick peek at it. We'll look at the southeast sector here quick. And you can see, just look at infrared. And I need to go over a little bit, don't I? All righty, southern Mississippi. Look how intense these storms are and how they're forming to the west. That's a cluster of storms that's developed there. It's not just one individual. So if you were in a location right here, for example, instead of just 30 to 60 minutes of thunder, you might be getting hours of it as they just keep building back to the west here. New ones firing back and going back over the same area. So you wind up with thunderstorms in different states of development in there. So you can see all the hazards you would be having if you were flying into this area. Tremendous downdrafts, hail possible, all kind of turbulence. I knew somebody that was a meteorologist that worked for Langley, NASA, and used to fly around thunderstorms to measure the turbulence. And he would talk about areas, even out in here, having extreme turbulence under the anvil. They'd be flying just to see what it was like, and they would wind up the plane even almost flipping over on them. So they were talking about the tremendous turbulence that you can get when you're flying around these storms. So obviously, the further away you can get from them, the better. One final thing I did want to show you, and what'll be right here on this, is dual pole. Something changed in radar a few years ago, and that the National Weather Service uses. It transmits, always had transmitted one pulse in the horizontal, out, bounces back to the radome. The transmit goes a lot longer than the receive. So transmit is very short, the receives much longer, it's picking up that signal back. But now, instead of going just a horizontal, it now does a horizontal and vertical. What that means is you can now measure the size of water droplets or size of snowflakes or hail. So you get some other cool things to look at here. Here's hail. What you're seeing here is the change in particle size. All these are about the same size. They're raindrops, big raindrops all around this area. And all of a sudden, right in here, they change size. You can see it bloomed in right here. And that's hail. Big hail probably coming down. So with this kind of radar, if you have dual pole radar, you can actually pick up hail. You can actually pick up debris from a tornado. So all these are things that you can utilize now from radar. I don't know what's exactly on your aircraft, but if you got access to this kind of radar, and these products are becoming more and more widespread and available, you can avoid areas where there's a hail shaft in your thunderstorms. So let me know if you have any questions about thunderstorms and local wind systems.